In this chapter, I talk about convergence, in other words, whether poorer countries are able to catch up with richer countries, and how we can analyze this by means of growth regressions. We start by recalling that the Solow model predicts that in case of two otherwise identical countries, the one that is poorer or farther away from the steady state and has a lower capital stock will grow faster. This prediction is called conditional convergence, and it is that conditional on sharing the same steady state, the country that is farther away from the steady state and has the lower capital stock will grow at a higher rate. So if two countries are similar to each other, the poorer country will be able to catch up with the richer one. However, if two countries differ fundamentally, for example in their saving rates, they would converge to different steady states. And in this case, it may not be the case that the poor country grows faster. It could be that the rich country grows faster because it is farther away from its steady state than the poor country from its steady state. And this is important. The Solow model does not predict absolute convergence, that the poor country will always grow faster than the rich country, but it only predicts conditional convergence, that conditional on sharing the same steady state, the poor country would grow faster. This can be illustrated with the Solow graph, where we have again capital per worker on the horizontal axis, output per worker on the vertical axis. We have the curve that is concave, the production function, output per worker as a function of capital per worker. We have the gross investment curve, that's the saving rate multiplied by income. That's what the economy invests. And we have the depreciation line from the origin, that's the capital per worker that depreciates at each moment. And since the production function is concave, we always have that these two curves intersect in the interior, and that's where the steady state is, where gross investment is equal to depreciation, and so the capital stock does not change anymore when we are here. Now, if we have a country that starts at K0, and it is away from the steady state, we know already gross investment is higher than depreciation, therefore capital will accumulate and the country will converge towards the steady state. And during this convergence, per capita income will also increase, but at a decreasing rate because the production function is concave. Now, suppose we have a second country here with the red dashed line that has a higher capital stock initially than the country with K0, but it converges to the same steady state, so it shares all the parameters with the first country. Then we know from the discussions on the Solow model that we had so far that this country with the higher capital stock accumulates capital typically at the lower rate, and at the same time, for a certain increase in capital, the increase in per capita GDP tends to be less than for the country that is farther away from the steady state, simply because the production function is concave. So as a consequence, if these two countries share the same steady state, the country that is closer to the steady state will grow more slowly than the country that is farther away from the steady state. So that is conditional convergence, and which is what the Solow model predicts. Now, however, suppose that this second country that is characterized by the initial capital stock K prime 0 has a different steady state because it has a higher saving rate. So it has a saving rate S prime. Then it converges to a different steady state associated with K prime star. Now we see here already, it's drawn like that still, although it is the richer country than the country with the capital stock K0, it is still farther away from its own steady state than the poorer country. And in this case, it could happen that it accumulates capital at a faster rate, and that this capital accumulation is so much faster than the capital accumulation of the poorer country that irrespective of the fact that the production function is concave here, per capita GDP still grows faster than per capita GDP of the poorer country. So that means we would not observe absolute convergence across countries. So it's not necessarily the case that the poorer country will always grow faster than the richer country. And this is also not what the Solow model predicts. The Solow model only predicts conditional convergence, so conditional on countries sharing the same steady state, but not absolute convergence, that irrespective of which steady states countries converge to, the poorer country would grow faster. Now, the rate of conditional convergence that the Solow model predicts is given by this expression here, and it is equal to 1 minus alpha, where alpha is the elasticity of output with respect to the production factor capital, multiplied by the population growth rate plus the rate of technological progress plus the rate of depreciation. So that's the rate of convergence, or in other words, the percentage by which the gap between the actual level of per capita GDP and the steady state closes each year. It's a rather complicated calculation to derive this rate of convergence, so I don't do it here. But what I want to do here is to show that for reasonable parameter values, such as a parameter value of 1/3 for alpha, which is due to estimates in the United States, population growth rate of 1%, which is a typical value that we observe, a rate of technological progress of 1%, which is also a typical rate that we can observe, and a rate of depreciation of 5%, which is also a standard value, we would get a rate of convergence of 4.5%. So that would be the prediction of a Solow model for reasonable parameter values. In the next few slides, we will see that empirical studies, however, typically find convergence rates that are lower, at around 2%. So how can we test the convergence hypothesis? An initial idea was to use a simple linear regression of the following specification, where we have on the left-hand side the difference in the logarithm of per capita GDP between an initial time period t0 and a final time period uppercase T. The difference in the logarithm would then be the growth rate of per capita GDP over the whole time period from 0 to uppercase T. And then regress this on a constant term, which would be the average growth rate of the country at the steady state, plus the initial level of per capita GDP, or the lag thereof, and an error term that it is assumed to be nicely behaved. In this case, what we would have is that a country that is poorer, if it grows faster, then the coefficient estimate for beta should be negative. And beta is the coefficient that we are interested in. It gives us actually the rate of convergence, as we will see on the next slide. However, this regression is the regression that tests for absolute convergence, and we will see the implications of this in a moment. Before we do so, let's spend a little bit of time on the interpretation of beta. If beta was equal to -1, then we would see on the previous slide that actually the log of initial per capita GDP would drop out of the equation. So if this is -1, then we see here it cancels off with this term here. And then that means that income levels actually at the date t are uncorrelated with initial differences. So that would mean that actually over this time period from t0 to uppercase T, full convergence takes place. So the poorer countries catch up with the richer countries completely. If beta is equal to 0, on the other hand, then we would see that the growth rates do not depend on initial per capita GDP. In this case, we would have no convergence at all. And if beta is in between -1 and 0, then the growth rates are negatively correlated with initial incomes. So then it would indeed be the case that poorer countries grow faster than richer countries. In this case, convergence would take place, and the speed of convergence is directly given by the parameter beta. However, the problem, as I already said, is that this regression does not test for conditional convergence. It tests for absolute convergence. And if we look at absolute convergence across countries, then we would find a scatter plot that looks like this. So here we would have 114 different countries observed between 1970 and 2015, where we plot the average growth rate during that time period here on the vertical axis, and on the horizontal axis we plot the logarithm of per capita GDP in 1970. And if we do such a regression, as we've seen it on the previous slides, then this would give us this dotted blue line. And we observe here that actually the coefficient for beta is not really significantly different from 0. So we do not find absolute convergence in the data. The poorer countries do not grow faster than the richer countries, and this coefficient beta is insignificantly different from 0. This, however, does not mean that the Solow model is wrong, because the Solow model does not predict absolute convergence. It predicts conditional convergence. Now, what can we do to test conditional convergence? Well, the first idea would be to eliminate all those countries that are so different from the other countries that they cannot be reasonably argued to converge to the same steady state. If we do so, and we eliminate all countries that are below a certain income level and only leave the richer countries, such as here the EU member states, Canada, the United States, Australia, New Zealand, and South Korea, then actually we would observe a highly significant negative coefficient estimate for beta. And indeed, among those countries, the countries that are poorer in terms of their logarithm of per capita GDP in 1970 tend to grow faster over the period from 1970 to 2015. So the growth rates of these countries are higher, and the growth rates of countries that started with an initially higher level of per capita GDP are lower. So this would mean that there is some indication that conditional convergence across similar countries takes place. So to summarize, across very different countries, the coefficient beta tends to be insignificant, and that means that there is no evidence for absolute convergence. However, across more homogeneous countries, beta tends to be significantly negative, so that there is evidence for conditional convergence. The economists Sparrow and Sala and Martin show in different papers that actually convergence is even stronger among regions within one country. So, for example, across the states in the US, or across the regions of the European Union, or across the prefectures of Japan, because these regions or states can reasonably be argued to converge to the same steady state at the country level. So they can reasonably be argued to be rather homogeneous. Now the question is, how can we test for conditional convergence also across very different countries? And the crucial idea here is to control for cross-country differences in the steady states. So control for differences in saving rates, in population growth rates, and so on and so forth, that could be reasonably argued to determine different steady states of different countries. And that's what we turn to next. Now this slide contains a conditional convergence regression, which is an expanded regression equation as compared to the one that we've seen previously. Still, we have the growth rate across countries I on the left-hand side between time 0 and time uppercase t. We still have the intercept alpha, and we have the log of initial per capita GDP with a coefficient estimate of beta 1 now, that is the conditional convergence estimate. And we have beta 1 here because we also include many control variables, basically the sum from k is equal to 2 to uppercase k, of all the variables that we think that they are correlated with steady state growth of a country. And then we have again an error term epsilon I that we assume to be nicely behaved. So here the beta k's are the partial correlation coefficients between the control variable k and the growth rate along the steady state or the long run growth rate. And I will say a few words on these coefficients on the next two slides. But we are particularly interested in the coefficient estimate for beta 1, which is the estimate of the speed of conditional convergence. And as I've said before, this tends to be significantly negative, and the coefficient size is around 0.02, which would mean that there is a rate of conditional convergence of 2%. So countries that are poorer close the gap to richer countries by 2% per year. Which variables are typically included in these convergence regressions? Well, I've already said the most important one, of course, and the one that we are interested in, is the log of initial per capita GDP. Its coefficient sign tends to be negative and significantly so, and the size of the coefficient tends to be around 0.02, which would mean a convergence rate of 2%. Then, average years of schooling and life expectancy are often included in these regressions, which tend to be positively correlated with growth. The log of the fertility rate tends to be negatively associated with growth. That's what we would expect from the Solow model, where the population growth rate shows up negatively. Government consumption could be expected to reduce investment, also shows up with a negative sign typically in these regressions. The rule of law and democracy indicators, they typically measure the quality of institutions and tend to be positively correlated with economic growth. Democracy squared is negative, which would mean that there is a non-linear relationship between democracy and economic growth, where the relationship is positive for low levels. So if a country becomes a democracy, this is very much positively correlated with economic growth, but at some level, kind of the positive correlation levels off. If a country is more open or has improvements in its terms of trade, that also tends to be positively correlated with growth. The investment ratio, as the Solow model would also predict, but inflation and corruption tend to be negatively correlated with economic growth. On the other hand, financial debt, so a better developed financial sector of an economy, also tends to be positively correlated with economic growth. Many other variables have been proposed. For example, the population size, which tends to be uncorrelated with economic growth, meaning that there is no indication of a so-called scale effect, where larger countries would grow faster than smaller countries. Student test scores are often seen as a better proxy for education than average years of schooling, and they tend to be positively related to economic growth. Infrastructure proxies also tend to be positively related to economic growth, and variables that are positively related to the quality of institutions also tend to be positively related to economic growth. By contrast, political instability, ethnic fractionalization are negatively related to economic growth. And then there are a number of geography-related variables, such as the latitude of a country. So the farther away a country is from the equator, typically the faster its growth rate is. If a country is landlocked, then it typically has a lower growth rate. If it has a larger share of arable land, that's positively related to economic growth. And also if it observes more rainfall, which tends to be positively related to agricultural productivity. But the variability of rainfall actually is negatively related to economic growth, because that increases the risk of severe weather events. Now, there are many problems related to these growth regressions. The most important one is that this method does not allow to analyze whether a certain variable causes economic growth. So, for example, it could just be that countries that grow faster can afford better institutions. And therefore, there would be a correlation, but it would not be that the better institutions cause economic growth. So there are issues with respect to endogeneity of the variables or omitted variables, because we can never control for all the control variables that would be relevant across the different countries, because we have way more potential control variables than we have countries. And of course, reverse causality, as I just said. So it could also be, for example, that people in a country that grows faster tend to be better educated because they can afford better education, or they tend to be healthier because they can invest more in their health. So we cannot claim causality based on the correlations that we've observed. The second issue is, as I already said, the number of potential regressors is much higher than the number of countries. So that means we can never ever include all the control variables and then apply certain procedures to reduce the dimensionality of the problem, which of course raises the potential for p-hacking, which kind of is related to this quote that if you torture the data long enough, it will confess. And everybody who has worked with these growth regressions knows that if you throw out some variables and include other ones, then the results change quite dramatically. And we never know, if we see a study, how many regressions the person who had performed the study carried out before finding the one that they put into the final paper that they've published. And that's a severe issue that has received a lot of attention also in the literature, because often you can just show whatever you want to show and come up with regressions that are consistent with your theory just by the simple fact that there are so many variables, and you can try out so many regressions that just by chance some of them will show the quote-unquote correct coefficients. Then it's often also the case that just different methods for estimation lead to very different results. That's particularly the case if convergence regressions are carried out based on panel data and dynamic specifications, where you include the lagged dependent variable as a regressor, and that's exactly what you would do if you want to test convergence in a panel data setting. Then you need the previous period's per capita GDP, and its coefficient would then allow to assess the rate of convergence. However, the inclusion of such a lagged dependent variable typically leads to a bias, and for this, as a remedy for this bias, different methods have been proposed in the literature. The problem is that the different methods tend to lead to very different results with respect to the estimation of this convergence rate in such a panel data setting. What can we do in these cases? There are some potential solutions, fortunately. For example, for the problem with causality, there are instances where we can do instrumental variable regressions, where we find a suitable instrument that we can use to address causality and to find causality with respect to a certain variable in these regressions. Sometimes co-integration analyses work when we have time series structure of the data, and sometimes randomized controlled trials can help in this context. With respect to the p-hacking issue, Bayesian regressions and lasso estimators can be used to isolate the relevant regressors in such specifications, and taking away leeway of the researchers themselves in order to design the specification in the model. So then Bayesian regressions and lasso estimators would do this more automatically and thereby take away some of the influence that the researchers could have on the final specification. And finally, Monte Carlo simulations can be used to assess the quality of different estimation methods in case of different specifications here with respect to panel data, and they can be used then to assess whether a certain estimator is a suitable estimator in the given context at hand.